Our universe is secretly woven together by an invisible architecture. Galaxies are not scattered randomly, but are linked in a colossal network known as the cosmic web. This hidden framework dictates the grand structure of everything we see, and holds profound secrets about where everything came from and where it is all headed. By the end of this journey, you will see the cosmos in a completely new light. We will uncover how astronomers trace these dark threads and confront the baffling forces that build this web. What do you think is the most profound connection in the cosmos? This grand design reveals a universe far more structured than we ever suspected. Think of the cosmic web as the universe's backbone, a vast architecture of invisible threads. Galaxies are not sprinkled randomly across the void. Instead, they cluster along these dense filaments like glitter scattered along the strands of a spiderweb, with unimaginably large, dark, and empty spaces stretching between them. These are the cosmic voids, regions of profound nothingness that can span hundreds of millions of light years. What sculpted this immense pattern? The answer lies with an unseen architect, dark matter. Although invisible and detectable only by its gravitational pull, dark matter forms an unseen skeleton. Over billions of years, its gravity acted like a cosmic glue, pulling ordinary matter into the intricate, web-like structure we observe today. To even begin to comprehend this process, astronomers turn to the most powerful supercomputers on Earth. These machines run simulations that rewind time, starting with the nearly smooth soup of the infant universe. They show how tiny, random fluctuations, ripples from the Big Bang itself, were amplified by gravity. Dense spots attracted more matter, growing into the nodes and filaments of the web, while the less dense regions emptied out, creating the voids. This web is not just a pretty pattern. It dictates the fate of galaxies, guiding their birth and growth along its bustling filaments. It even imprints itself on the oldest light in the universe, the cosmic microwave background, leaving a faint but detectable signature. This grand design is truly the foundation of everything we see. And if this is the architecture, what strange materials is it built from? What is the true nature of the dark matter that holds it all together? That invisible architect, dark matter, is the universe's most influential ghost. We cannot see it, touch it, or detect it with any telescope, yet its gravitational hand has sculpted the entire cosmic web. Think of it as the hidden framework of a colossal building, while the galaxies we see are merely the lights flickering on inside. Without this unseen skeleton, the glittering cities of galaxies would never have gathered along those dark filaments. The universe would be a formless, dim sea of scattered gas, a place without grand structure or design. So how do we know this ghost is even there? We witness its effects. When astronomers measure how fast stars orbit the centers of galaxies, they find something bizarre. The stars on the outer edges move just as fast as those near the center. According to the laws of gravity, this should be impossible. It is as if the entire galaxy is embedded within a massive, invisible sphere of matter, a dark halo whose gravity is spinning the whole structure. We see its hand again in a phenomenon called gravitational lensing. The immense gravity of a dark matter halo can warp the fabric of space itself, bending the light from distant galaxies behind it like a cosmic magnifying glass. This creates distorted, stretched, and sometimes multiple images of those faraway objects. By studying these funhouse mirror reflections, we can literally map the distribution of the invisible stuff. This mysterious substance makes up roughly 27% of everything in the cosmos, a dominant force that has been pulling ordinary matter into its web for billions of years. It is the great organizer, the silent builder whose nature remains one of physics' most profound mysteries. But if dark matter is the framework, what is the glue that flows along its threads, bringing it all to life? So we are left with a ghost, and must find a way to take its picture. Mapping the invisible cosmic web is a feat of modern astronomical detective work. One of the most powerful techniques is the redshift survey. When a galaxy moves away from us, its light stretches, shifting toward the red end of the spectrum. By measuring this redshift for millions of galaxies, astronomers can calculate not only their distance from Earth, but also their velocity. This creates a three-dimensional map of the universe, a pointillist painting of cosmic structure. Projects like the Sloan Digital Sky Survey have done exactly this, plotting the positions of countless galaxies to reveal the stunning, filamentary architecture of the web in breathtaking detail. You can actually see the dense knots where galaxies cluster and the long, dark threads connecting them across the void. But that is only one piece of the puzzle. Another method peers back to the very beginning, to the faint afterglow of the Big Bang known as the cosmic microwave background. As this ancient light travels through the cosmic web on its journey to us, it is subtly altered. The gravity of the web's dark matter filaments imprints a faint signature, a slight cooling or heating, which can be detected like a shadow on the oldest photograph of the universe. And then there is gravitational lensing, where we watch the invisible warp the visible. The immense mass of a dark matter filament bends the light from galaxies behind it, creating tiny, distorted arcs. By studying these distortions, we can literally trace the outline of the unseen, mapping the dark skeleton directly. The sheer volume of data from these methods is staggering, requiring the world's most powerful supercomputers to process. These machines run simulations that model the universe's entire evolution, testing our theories of how this vast network came to be. They are the virtual time machines that bring the unseen into brilliant, simulated focus. Yet for all this technological marvel, a deeper mystery now tugs at the edges of this grand design. What force is acting upon the web itself, stretching the very fabric of the cosmos and dictating its ultimate fate? That same force stretching the cosmos also pulls at the web's very threads. Dark energy is the mysterious agent behind the universe's accelerating expansion, and its influence reaches deep into the architecture of the cosmic web. Imagine the universe as a loaf of raisin bread rising in the oven. The dough represents space itself, and the raisins are clusters of galaxies. As the dough expands, all the raisins move away from each other. Now imagine the oven suddenly gets hotter, and the bread begins to rise faster and faster. This is the effect of dark energy. It is causing the very fabric of space to stretch at an ever-increasing rate. For the cosmic web, this means the vast filaments that connect galaxy clusters are themselves being stretched and pulled taut over time. The distances between the great nodes of the web grow larger, and the delicate threads of dark matter that bind them become thinner, like strands of cosmic taffy. On the largest scales, this repulsive force of dark energy directly counteracts the attractive pull of gravity. Gravity works to pull matter together, to build structure, while dark energy works to drive it apart, to dilute the universe. This creates a cosmic tug-of-war that will ultimately decide the fate of everything. Will gravity manage to hold the web together, or will dark energy eventually win, stretching the cosmic architecture so thin that galaxies become isolated islands in an ever-cooling void? This dynamic interplay is not some distant future event. It is happening right now, influencing how galaxies move within the web and how they interact with their neighbors. As the filaments stretch, the flow of gas that fuels star formation can be slowed or even cut off, altering the life cycle of galaxies. Understanding this balance is perhaps the greatest challenge in modern cosmology. It forces us to ask, if dark energy is reshaping the grandest structures in existence, what subtle marks is it leaving on the galaxies that call this web home? These galaxies are not solitary islands but vibrant cities within a vast, interconnected empire. Each one acts as a crucial node in the cosmic network, tethered to its neighbors by the invisible threads of dark matter and the flowing rivers of intergalactic gas. These connections are not passive lines on a map. They are dynamic conduits, highways for the flow of the raw materials that build stars and power galactic engines. A galaxy's position within this network dictates its entire destiny. At the busy intersections where multiple filaments cross, galaxies are drawn together by immense gravity, piling up into colossal clusters containing thousands of individual galaxies. These are the metropolitan hubs of the cosmos, places of intense activity and dramatic collisions. In these dense environments, galaxies are constantly interacting, their shapes distorted and their gas stripped away, which can either trigger furious bursts of new star formation or quench it entirely. The traffic along these cosmic highways is relentless. Vast reservoirs of cool gas, the fuel for new stars, flow along the dark matter filaments and pour into the waiting galaxies at their nodes. This steady supply line allows galaxies to grow, to build new generations of stars, and to light up the darkness. But what happens to a city cut off from all supply routes? Look to the cosmic voids, the immense empty spaces between the web's strands. Here, galaxies are truly isolated. They are like lonely outposts in a desert, disconnected from the nourishing flows of gas. Often, these void galaxies are smaller, quieter, and more primitive. Without a constant influx of new material, their star formation sputters out early, leaving them as faded relics of a busier past. By simply mapping a galaxy's address within this cosmic web, astronomers can infer so much about its life. Is it a bustling giant in a dense knot, or a quiet, aging hermit in a vast emptiness? This nodal perspective reveals that a galaxy's story is not written in isolation. It is a story written by its connections, by the invisible roads it sits upon. And if the galaxies are the cities, then we must ask, what is the nature of the roads themselves? What secrets are carried along those dark, flowing filaments? These filaments are the universe's great superhighways, flowing with the raw material of creation. They are not empty tunnels but dense, thread-like rivers of dark matter and hydrogen gas, stretching across unimaginable voids for hundreds of millions of light years. Picture the largest structure you can conceive, a bridge of pure gravity connecting entire galactic cities, and you are still only grasping a fraction of their true scale. Within these cosmic thoroughfares, gravity is the relentless engine. It pulls galaxies along these filaments like cars on a freeway, funneling them toward the dense, bustling intersections where they will merge into colossal clusters and superclusters. This journey is not a gentle cruise. It is a violent, transformative process. As galaxies are herded together, their close encounters can trigger massive bursts of new star formation, igniting the gas within them into a firestorm of stellar birth. Other times, the gravitational turmoil can strip a galaxy of its gas entirely, leaving it a barren, red, and dying world. The filament itself is alive with activity. Vast reservoirs of intergalactic gas, cooled and condensed over billions of years, flow along these dark channels. This gas is the lifeblood of galaxies, the primary fuel for new stars. When this river of matter pours into a galaxy sitting at a filament's node, it can rejuvenate the entire system, sparking a new era of light and heat. By studying these highways, astronomers can predict a galaxy's future. Is it heading toward a chaotic merger, or is it receiving a steady supply of fuel that will keep its stellar factories running for eons? The answer is written in the invisible flow of the filament it calls home. But what exactly is flowing along these dark roads? What is the nature of the intergalactic gas that gives life to the cosmos? This intergalactic gas is the universe's raw, unformed potential. It is a vast, diffuse sea of primordial hydrogen and helium, the original elements forged in the first few minutes after the Big Bang. This gas fills the immense filaments of the cosmic web and hangs, thin and quiet, within the great voids. It is the fundamental building block from which all stars and galaxies are born. But this gas is not static. It cycles continuously through the web, a great conveyor belt of creation driven by the relentless pull of gravity. When this river of gas flows along a dark matter filament and pours into a dense galaxy cluster, the results are spectacular. The sudden influx of fuel can trigger firestorms of star formation, lighting up entire galaxies in a blaze of stellar birth. In other cases, the gas feeds directly into the supermassive black holes that lurk at the centers of galaxies. As this material spirals into the abyss, it heats to incredible temperatures, causing the black hole to flare with the intensity of a billion stars, becoming what we call a quasar. These are the most luminous objects in the universe, powered by the simple act of intergalactic gas falling home. Yet for all its importance, this gas is incredibly difficult to see. It is so diffuse that it emits very little light of its own. To detect it, astronomers must use specialized instruments, like ultraviolet telescopes in space. They look for the subtle ways this gas absorbs the light from distant, brilliant objects like quasars, casting a faint fingerprint that reveals its presence and composition. Mapping this invisible ocean is essential. We must understand how much gas is out there, where it is flowing, and how it cools and condenses to truly model the cosmic web's dynamic life cycle. And this gaseous sea does not travel alone. Its journey is shaped by the pull of gravity and pushed by the pressure of another hidden force, one that weaves through the entire cosmos. This gaseous component interacts with another mysterious element, cosmic magnetic fields. Woven through this gaseous sea are invisible lines of force, cosmic magnetic fields that stretch across the void. These fields are not mere decorations. They are a fundamental part of the web's structure, influencing nearly everything that happens within it. Generated by violent cosmic engines like merging galaxies and the supermassive black holes at their hearts, these magnetic fields are then stretched and pulled by the same gravitational forces that shape the web itself. They align along the vast filaments, creating a ghostly roadmap that guides the flow of charged particles. This magnetic guidance system acts like a set of cosmic rails, channeling the rivers of ionized gas as they travel along the filaments. It can even influence the collapse of giant gas clouds, nudging the process of star formation in subtle but crucial ways. Without these fields, the chaotic energy from supernova explosions and quasars might tear gas clouds apart before they could ever coalesce into new stars. The fields provide a form of structure and pressure, helping to maintain the stability of entire galactic disks as they spin through the darkness. How do we begin to see something so fundamentally invisible? Astronomers use sophisticated radio telescopes to detect the faint whispers of these fields. When charged particles like electrons spiral along a magnetic field line, they emit a specific type of polarized radio wave. By carefully mapping this synchrotron radiation across the sky, we can trace the outlines of these immense magnetic structures, revealing their intricate patterns woven into the cosmic tapestry. This magnetic influence extends even to the most energetic travelers in the universe. Vast streams of high-energy particles, known as cosmic rays, constantly bombard our galaxy. These rays do not wander randomly. They are funneled and accelerated by the web's magnetic fields, their paths bent and twisted as they journey from distant, explosive sources. This interplay adds a profound layer of complexity to our models, showing that the cosmic web is not just a structure of mass and gravity, but a dynamic system infused with invisible forces. And if magnetic fields can guide the most energetic particles in the cosmos, what other unseen messengers are traveling these ancient roads, carrying secrets from the deepest voids? These cosmic rays are the universe's most energetic travelers, atomic fragments accelerated to nearly the speed of light. They are not wandering aimlessly. Their chaotic journeys are dictated by the unseen architecture of the cosmic web. Born in the violent hearts of exploding stars and the furious jets of supermassive black holes, these particles are then cast adrift into the vast intergalactic medium. Here, their paths are no longer straight. The magnetic fields woven through the web's filaments act like a colossal maze of invisible curves and bends. A single proton, carrying more energy than a professional baseball pitch, can have its trajectory completely twisted by these fields, turning its voyage into a random, unpredictable walk across millions of light years. This is why we often cannot trace a cosmic ray back to its original source. By the time it reaches us, its path is a tangled mess, a testament to the complex magnetic environment it has endured. Yet, this very chaos holds a key. The distribution of cosmic rays arriving at Earth is not perfectly even. Scientists find subtle patterns, slight overdensities and underdensities in the directions from which they come. These patterns are not random. They are a coded message, a shadow map of the magnetic fields and matter distribution they have passed through. Dense filaments, with their stronger and more tangled magnetic fields, will scatter these particles more effectively than the relatively empty and magnetically quiet voids. By reading this cosmic cipher, astronomers can infer the structure of the invisible magnetic web itself. This research reaches far beyond pure curiosity. Understanding how these high-energy particles are channeled and accelerated is crucial for unraveling the most powerful astrophysical explosions. It also poses a very practical question for our future. For astronauts traveling beyond the protective bubble of Earth's magnetic field, these cosmic rays represent a genuine hazard, a persistent rain of radiation that could threaten long-duration missions to Mars or beyond. By modeling how the web influences their flow, we can better predict these risks and perhaps one day find safer routes through the cosmic sea. The web does not just shape galaxies and gas, it steers the very bullets of deep space. And if it can bend the paths of matter, what does it do to the light that brings us our view of the cosmos? The same invisible architecture that bends the paths of cosmic rays also warps the very fabric of light. Gravitational lensing is a direct window into the unseen, a phenomenon where the gravity of a massive object acts like a cosmic magnifying glass. When light from a distant galaxy travels toward us and passes near a dense knot in the cosmic web, like a massive galaxy cluster, the cluster's immense gravity curves the space around it. This warping of spacetime bends the light's path, distorting and often magnifying the image of the background galaxy. It is as if we are looking at the distant universe through the bottom of a grand, cosmic wine glass, where the light is stretched and twisted into faint, luminous arcs. This effect comes in two distinct forms, each revealing a different layer of the web's structure. Strong lensing happens around the most massive clusters, where the gravitational pull is so intense that it can create multiple, mirrored images of a single background galaxy, or stretch it into a perfect, thin ring of light known as an Einstein ring. These dramatic events allow astronomers to map the total mass of the cluster, including the vast halo of dark matter that holds it together. But the web's true skeleton is revealed through weak lensing. Across the sky, the subtler gravity of the dark matter filaments themselves causes a far more delicate distortion. It does not create rings or multiple images. Instead, it imparts a tiny, coherent shear to the shapes of millions of background galaxies, stretching them all in a direction that traces out the invisible filament. Individually, each distortion is minuscule, almost imperceptible. But by studying the patterns across vast surveys of countless galaxies, astronomers can statistically map the grand architecture of the dark web itself. They can trace the outline of a filament not by seeing it, but by seeing how it gently warps the light from everything behind it. This technique has become one of our most powerful tools for cosmic cartography. It allows us to probe the distribution of mass directly, confirming that the great voids are truly as empty as they seem, while the filaments are dense with unseen matter. Through the lensing effect, the cosmic web casts a shadow made not of darkness, but of distorted light, providing our clearest picture yet of the universe's hidden dimensions. These virtual universes are our greatest laboratories for exploring the cosmic web. Scientists build entire cosmos inside the world's most powerful supercomputers, using codes with names like Illustris and Millennium. They begin with the raw ingredients of the early universe, a nearly smooth soup of dark matter and gas, seeded with the tiny, random fluctuations we see in the cosmic microwave background. Then they set the rules, the known laws of physics, and press play. Over billions of simulated years, gravity takes over. Those tiny ripples amplify, with dense spots pulling in more and more matter. You can watch it happen, a mesmerizing dance of particles coalescing into the first faint threads, which then thicken and connect, weaving the very same filamentary structure we observe in the real night sky. This is not just a pretty animation. It is a profound validation of our entire cosmological model. The fact that these simulations, running only on the physics we understand, can recreate the grand design of the universe so accurately tells us we are fundamentally on the right track. Dark matter must behave as we think it does, and gravity must work on the largest scales exactly as Einstein predicted. But these digital realms do more than just confirm what we already know. They act as prophetic tools, predicting phenomena that telescopes have not yet spotted. A simulation might reveal that gas flowing along a filament should reach a specific temperature, or that tiny, dark satellite galaxies should orbit larger ones in a distinct pattern. These predictions become treasure maps for observers, guiding them where to look and what to look for in the vastness of space. The cycle is continuous and powerful. Astronomers collect new data from redshift surveys and lensing studies. Then they feed that data back into the simulations. They tweak the parameters, asking what if dark matter is slightly different? What if dark energy changes over time? By running these countless experiments, these virtual universes become a testing ground for the most radical ideas in physics, helping us refine our understanding of the cosmos one line of code at a time. They are our best window into the unseen forces that built our home, and the ultimate tool for probing the limits of our own knowledge. What new mysteries will these simulated worlds reveal next? The blueprint for the entire cosmic web was imprinted on the universe in its first fleeting moments. Those initial conditions, a nearly smooth sea of primordial plasma, were not perfectly uniform. Tiny, random quantum fluctuations, smaller than a single atom, were stretched to cosmic proportions during a period of hyper-expansion known as inflation. These minute ripples in density, these seeds of future structure, are what we now see frozen in time as the cosmic microwave background. That faint afterglow is a cosmic treasure map, its hot and cold spots directly corresponding to the regions that would, over billions of years, collapse into vast voids or condense into the great filaments. Gravity was the patient sculptor. It relentlessly worked on these imperfections, pulling ever so slightly more matter toward the slightly denser spots. As the universe expanded and cooled, dark matter, which does not interact with light, began to clump first, forming a hidden scaffold. Ordinary matter, the hydrogen and helium gas, was then pulled into this growing dark matter skeleton. The first structures to emerge were not grand galaxies, but faint, thread-like wisps of dark matter, the earliest filaments of the cosmic web. Then came the lights. A few 100 million years after the Big Bang, the first stars and galaxies ignited, unleashing a transformative era known as reionization. Their intense ultraviolet radiation blasted through the cosmos, heating and tearing electrons away from the neutral hydrogen gas that filled the universe. This process fundamentally changed the nature of the intergalactic medium. The gas became ionized, hotter, and more resistant to collapsing into new structures. It was a cosmic feedback loop, where the first objects carved out their own spaces, permanently influencing how and where future generations of galaxies could form. The web was no longer a silent, dark structure. It was now a dynamic arena, its evolution driven by both the relentless pull of gravity and the brilliant, disruptive energy of the first stars. How did these earliest threads of darkness and light eventually weave themselves into the magnificent galactic metropolises we see today? Long before the first galaxies flickered on, the cosmic web existed as a ghostly blueprint. These were not the brilliant filaments we see today, but their primordial ancestors, vast overdensities of dark matter and gas known as proto-filaments and proto-clusters. In this shadowy dawn era, the universe built its structure from the ground up through a process called hierarchical clustering. Imagine tiny specks of dark matter, drawn together by their mutual gravity, merging to form small clumps. These clumps then found one another, colliding and combining to build ever larger structures. It was a cosmic snowball effect, where small villages of matter gradually coalesced into the great cities and superhighways of the dark web. Nestled within these dense, primordial knots, the very first stars ignited. These were not like the stars of today. They were behemoths, hundreds of times more massive than our Sun, burning ferociously bright and dying young in colossal supernova explosions. Their deaths seeded the cosmos with the first heavy elements, and in their wake they left behind the seeds of the first black holes. This was not a peaceful construction site. The intense radiation and powerful shockwaves from these first stars and black holes acted as cosmic feedback, heating the surrounding gas and blowing it away from the densest regions. This feedback could stifle the birth of the next generation of stars, or it could trigger new waves of collapse by compressing neighboring gas clouds. It was a dynamic, chaotic ballet where creation and destruction danced together to shape the growing web. To witness this epoch, we must look back over 13 billion years. This is the mission of telescopes like the James Webb Space Telescope, which peers into the deep infrared, collecting the faint, stretched light from this infant universe. By studying the distribution and properties of the earliest galaxies it can detect, Webb is essentially mapping the underlying dark matter proto-filaments they are embedded within. The specific arrangement, the thickness, and the density of those first threads set the rules for everything that followed. They determined how efficiently gas would flow, where the most massive clusters would arise, and ultimately, what kinds of galaxies would form. The entire future complexity of the cosmic web was encoded in the subtle properties of these primordial structures. So how did these initial dark threads and glowing knots finally weave themselves into the brilliant galactic empires we recognize today? A galaxy's life story is written by its address within the cosmic web. This vast network does far more than simply arrange galaxies in space. It dictates their very nature, their growth, and their ultimate fate from birth to old age. The environment a galaxy calls home imprints itself on everything from its shape to its star-forming activity. Consider a galaxy fortunate enough to reside along a busy, dense filament. This location is a cosmic hub of activity, with rivers of fresh gas constantly flowing in and frequent, dramatic encounters with neighboring galaxies. These galactic mergers are transformative events. When two galaxies collide, their gravitational dance churns up the vast reservoirs of gas within them, compressing the material and igniting firestorms of new star formation. The galaxy swells in size and brilliance, its spiral arms glowing with the blue light of millions of young stars. This is a place of rapid growth and dynamic change. But travel out to the great cosmic voids, the immense and empty deserts between the web's strands. Here, a galaxy lives in profound isolation. Cut off from the nourishing flows of intergalactic gas and spared from dramatic collisions, its evolution is slow and quiet. The frantic star formation of its youth sputters out early. Its stellar population ages gracefully, its light shifting to the red as its massive, blue stars die off, leaving behind a quieter, older population of longer-lived stars. These void galaxies are often living fossils, preserving a glimpse of an earlier, simpler cosmic era. The web's influence even extends to a galaxy's fundamental architecture. Those majestic spiral galaxies with their graceful, pinwheeling arms are most often found along the filaments. The steady, ordered flow of gas along these highways helps maintain their disguised structure. But in the dense, chaotic urban centers of galaxy clusters, where mergers are common and gravitational interactions are violent, a different shape dominates. The elegant spirals are stripped and scrambled, their gas torn away, their stars thrown into random orbits. They are transformed into featureless, round or elliptical galaxies, where star formation has been effectively shut down. By simply mapping a galaxy's position in this cosmic network, astronomers can read its biography. They can tell if it grew through a series of violent mergers or led a quiet, solitary life. This environmental dependency solves a long-standing mystery, explaining the incredible diversity of galaxies we see when we look up at the night sky. But this relationship is not a one-way street. As these galactic cities grow and change, they send powerful feedback out into the web that shaped them. These brilliant galactic cities give back as much as they take. The cosmic web is not a rigid sculpture, but a living ecosystem, and galaxies are its most powerful engines of change. Through colossal explosions and unimaginable outpourings of energy, they actively reshape the very environment that birthed them. This process is known as feedback, and it is the key to understanding why the universe looks the way it does. When a massive star reaches the end of its life and explodes as a supernova, it does more than just create a brilliant flash. It unleashes a titanic shockwave that ripples through its host galaxy and beyond, violently heating the surrounding gas and blasting it out into the vast intergalactic space. This heated gas becomes too energetic to collapse and form new stars, effectively putting a brake on star formation in that local neighborhood. On an even grander scale, the supermassive black holes at the centers of galaxies can become active galactic nuclei. As these monsters feed, they unleash furious jets of radiation and charged particles that can travel for millions of light years. These jets carve enormous bubbles in the surrounding intergalactic gas, pushing it aside and preventing it from cooling and flowing into other galaxies. In this way, a single active black hole can dictate the growth of an entire galactic cluster, quenching star formation across a vast region. Yet feedback is not always destructive. The very same shockwaves that heat gas in one area can compress cold, dense gas clouds in another, triggering the birth of new stars in a nearby galaxy. It is a dynamic and self-regulating cycle. This intricate dance between creation and destruction solves a major cosmic puzzle. Without feedback, our simulations show that galaxies would grow far too large, too quickly, consuming all available gas and forming stars at a frantic, unsustainable rate. The cosmic web would look completely different. Feedback acts as a cosmic pressure valve, releasing energy to maintain a delicate balance. It ensures that some gas remains hot and diffuse in the filaments and voids, while other pockets are allowed to cool and condense into new stellar generations. This reciprocal relationship means the web and its galaxies grow together, in a constant, energetic dialogue. The great cosmic architecture is not silent. It hums with the feedback of a trillion stellar engines, each one leaving its mark on the flowing rivers of creation. But even with all these galactic engines and feedback loops, a simple cosmic inventory has stubbornly refused to add up. Astronomers know precisely how much ordinary matter, the stuff of stars, planets, and you and me, should exist in the universe based on measurements of the Big Bang's afterglow. Yet when they tally up all the visible matter locked in galaxies and clusters, more than half of it is simply missing. This is the great missing Baryon problem, one of the most persistent puzzles in modern cosmology. So where did it all go? The leading suspect is the cosmic web itself. Theorists predicted that the majority of the universe's ordinary matter would not be in the brilliant galaxies, but spread thinly throughout the vast, dark filaments as a diffuse, superheated gas. This is the warm, hot intergalactic medium, a ghostly ocean of matter so tenuous and so hot that it is completely invisible to ordinary telescopes. To find it, astronomers had to become detectives of the light. They turned their most powerful instruments toward the brightest beacons in the distant universe, quasars. As the intense light from a quasar travels billions of light years to reach us, it passes through these invisible filaments. The specific wavelengths of light that are absorbed by the superheated gas in these filaments create a unique fingerprint, a barcode of missing lines in the quasar's spectrum. By decoding this absorption signature, scientists have finally confirmed the presence of the long-sought matter, hiding in plain sight within the web's architecture. This discovery does more than just complete a cosmic checklist. It powerfully validates our entire understanding of how the cosmic web formed and evolved. The simulations predicted that gravity would pull most of the ordinary matter into these vast, filamentary reservoirs, and the observations now spectacularly confirm it. The search for the missing baryons demonstrates that the cosmic web is far more than a beautiful structure. It is a fundamental component of the universe's mass budget, and the key to solving some of cosmology's most profound mysteries. This hidden ocean of gas is the final piece of the puzzle, the dark, flowing blood that gives the cosmic skeleton its life. This ghostly architecture betrays its presence through subtle imprints on everything we can see. While the cosmic web itself is woven from darkness, it constantly interacts with light, matter, and radiation, leaving behind a collection of faint but detectable signatures. The most direct evidence comes from the grand arrangement of galaxies themselves. Massive redshift surveys have painstakingly mapped the three-dimensional positions of millions of galaxies, revealing the stunning, large-scale pattern of dense clusters linked by delicate filaments and separated by vast, empty voids. This distribution is not random. It is the visible footprint of the underlying dark matter skeleton, the glitter tracing out the shape of the hidden web. Another signature is etched into the oldest light in the universe, the cosmic microwave background. As this ancient afterglow travels for billions of years to reach our telescopes, it passes through the evolving web. The gravity of the dark matter filaments subtly warms or cools the light, creating a specific pattern of minute temperature variations. It is like finding the shadow of a vast, invisible tree cast upon the first light of dawn. Then there is the powerful tool of gravitational lensing, where we observe the web not by what it emits, but by how it bends the light from galaxies behind it. The combined gravity of a dark matter filament acts as a weak lens, imparting a tiny, coherent stretch to the shapes of countless background galaxies. By analyzing the collective distortion of millions of these faint smears of light, astronomers can trace the outline of the invisible filament with remarkable precision. To capture these subtle signals, we have launched ambitious missions like the Dark Energy Survey and the Euclid Space Telescope. These projects are not looking for single brilliant objects. They are cosmic cartographers, designed to meticulously survey huge swaths of the sky, measuring the shapes and redshifts of billions of galaxies to build the most detailed map of the cosmic web ever conceived. Each observational technique provides an independent line of evidence. The galaxy distribution shows us where the mass is, the lensing distortions show us how much mass is there, and the cosmic microwave background tells us about the primordial seeds from which it all grew. When combined, these different pieces of the puzzle cross-check and reinforce each other, allowing scientists to constrain and refine our theoretical models of the universe. This multi-messenger approach is crucial because a mystery as profound as the cosmic web cannot be solved with a single glance. Our view of this hidden architecture grows clearer and more detailed with every technological leap, bringing the universe's grand design into ever sharper relief. Our cosmic cartography is about to leap forward with a new generation of eyes on the sky. These are not merely larger telescopes. They are entirely new instruments designed to perceive the universe in ways we once thought impossible. The James Webb Space Telescope, with its infrared gaze, is already looking back to the era of the very first galaxies, seeing them not as isolated points of light, but as glowing markers embedded within the primordial dark matter filaments. It is tracing the web's infant structure, revealing how those first threads were woven. Soon, it will be joined by the Nancy Grace Roman Space Telescope, a wide-field surveyor that will map the cosmos at an unprecedented speed and scale. Roman will not study one galaxy at a time, but millions, creating a staggeringly detailed three-dimensional chart of the cosmic web's architecture, and measuring the subtle distortions of weak gravitational lensing with phenomenal precision. This will give us our clearest picture yet of how dark matter is distributed across the vast expanses of space. On the ground, the square-kilometer array will use thousands of radio antennas to listen to the universe. It will detect the faint radio whispers of neutral hydrogen gas, the primary fuel of the cosmos, allowing us to trace its flow along the cosmic filaments with incredible detail. This will be like watching the weather patterns of the intergalactic medium, seeing how the great rivers of gas are channeled and where they pour into hungry galaxies. These missions are also poised to unravel the web's magnetic personality. By mapping the polarization of radio waves across the sky, they will finally chart the vast, invisible magnetic fields woven through the filaments, understanding how these forces guide cosmic rays and shape the birth of stars. This global effort is a testament to international collaboration, with scientists and engineers across the world pooling knowledge and resources to tackle the universe's grandest mysteries. The data flowing from these observatories will be a fire hose of discovery, fueling supercomputer simulations that are more realistic than ever before. We are not just building better maps, we are constructing a deeper understanding, one that will inevitably challenge our theories and reveal cosmic phenomena we have not yet even dreamed of. Even with our most advanced maps and simulations, the cosmic web resists full explanation. The profound mystery of dark matter remains at the heart of the puzzle. We know its gravitational pull sculpts the web, but we have no idea what it actually is. Is it a sea of exotic, undiscovered particles, or does it require a fundamental rewrite of the laws of gravity themselves? This uncertainty creates a major gap in our understanding. Without knowing dark matter's true properties, we cannot accurately predict how the web's fine, thread-like structures should behave over billions of years. Are these filaments stable, or do they slowly fray and dissolve under the relentless tension of dark energy? The same is true for dark energy, the force driving the cosmic expansion ever faster. We do not know if its strength is constant or if it changes over time, a question that directly determines the ultimate fate of the entire web. Will it stretch this cosmic architecture into a thin, cold haze, isolating every galaxy forever? Our most sophisticated computer simulations highlight these very problems. When scientists run these virtual universes, they sometimes find a disconnect between the model and reality. A simulation might produce too many small satellite galaxies around a large spiral like our Milky Way, or it might struggle to recreate the exact distribution of gas temperatures observed within real filaments. These are not mere programming errors. They are glaring signs that our models are missing a crucial piece of physics. Perhaps dark matter particles interact with each other in ways we have not accounted for. Or maybe the feedback from stars and black holes is even more complex than we thought. Solving these riddles demands a radical collaboration of minds: particle physicists working with underground detectors, theorists exploring new ideas of gravity, and astronomers analyzing new telescope data must all combine their insights. This grand, interdisciplinary quest is what drives the field forward, pushing us to build better telescopes and more powerful supercomputers. The unresolved nature of the cosmic web is not a failure of science, but its greatest inspiration, compelling a new generation to look deeper into the darkness and ask the next great questions. This hidden web reveals its secrets not just through light, but through a chorus of invisible messengers. Multi-messenger astronomy is the next great leap in cosmic exploration, an approach that listens to the universe as much as it looks at it. Instead of relying solely on traditional telescopes, scientists now combine observations of light with detections of gravitational waves, neutrinos, and cosmic rays. Each of these messengers carries a unique piece of the puzzle, and together, they are giving us our first multi-sensory view of the cosmic web. When two black holes collide in the depths of space, they do not produce a flash of light, but they violently shake the fabric of spacetime itself, sending out ripples known as gravitational waves. By pinpointing the location of these cataclysmic mergers, we can place them on our map of the cosmic web. Are these collisions happening more often in the dense nodes of galaxy clusters, or out along the lonely filaments? The answer tells us how the web's architecture influences the most powerful events in the universe. Meanwhile, nearly massless particles called neutrinos stream through the cosmos almost completely unimpeded. These ghostly particles are created in the most ferocious environments, like the superheated gas within filaments that is being shocked and accelerated. By tracing the path of a high-energy neutrino back to its source, we might be able to follow it directly to a violent process occurring within a specific filament, essentially using it to illuminate a dark road on our cosmic map. Even the chaotic paths of cosmic rays become a valuable tool. As we learned, their twisted journeys are dictated by the web's magnetic fields. By analyzing the patterns of cosmic rays that arrive at Earth from different directions, we can reverse engineer the structure of those invisible magnetic fields woven through the filaments, mapping the cosmic rails that guide the flow of matter. The true power comes from correlation. A single event, like a distant supernova, might be seen as a flash of light by a telescope, detected as a burst of neutrinos by an underground lab, and later followed by a shower of cosmic rays. By stitching these different signals together, scientists can build a holistic, three-dimensional model of the event and its environment within the web. This approach is still in its infancy, but it promises to uncover aspects of the cosmic network that are completely invisible to light alone. It is the difference between looking at a photograph of a city and then walking its streets, hearing its sounds and feeling its vibrations. We are no longer just mapping the web's skeleton. We are beginning to feel its pulse. That initial blueprint for the cosmic web was drawn in a fraction of a second. The universe's first moments were marked by a phenomenal growth spurt known as cosmic inflation, a period of exponential expansion that stretched a subatomic speck of space to a size larger than our observable universe. During this incredible event, the empty vacuum of space itself was fizzing with quantum activity, bubbling with tiny, random fluctuations in energy. As inflation violently stretched the fabric of reality, it stretched these minute quantum ripples along with it, magnifying them from the microscopic to the cosmic. Those amplified wrinkles in density became the very seeds for all future structure. The slight overdensities and underdensities that gravity would later work on for billions of years to build the great filaments and vast voids. This theory makes a precise prediction about what the infant universe should look like, and we have observed its signature directly. The cosmic microwave background, that fossilized light from the universe's infancy, is not perfectly smooth. It is modeled with a specific pattern of hot and cold spots, a telltale fingerprint of those primordial density variations. Space missions like the Planck satellite have mapped this pattern with exquisite precision, and its statistical properties match the predictions of inflation with stunning accuracy. The specific scale and the subtle symmetry of the cosmic web we see today, the way filaments seem to form a network of certain dimensions, are a direct consequence of the physics that governed that first, fleeting moment of inflation. This connection is profound because it links the realm of the unimaginably small, the quantum world, to the grandest structures in existence. The same physics that describes subatomic particles must also account for the architecture of the cosmos. By studying the web, we are indirectly probing the energy scales of the universe's birth, an era so remote that no telescope will ever see it directly. The cosmic web is more than a structure. It is a time capsule, preserving the echo of inflation's thunderous expansion and offering us a unique bridge across nearly 14 billion years of cosmic history. This grand cosmic architecture challenges our very sense of place. We are accustomed to thinking of our home as a single galaxy, the Milky Way, a brilliant island in a dark sea. The reality revealed by the cosmic web is profoundly different. Our galaxy is not an island at all, but one single node in a sprawling, interconnected metropolis, linked by invisible threads to countless other cities of stars. This perspective is both humbling and awe-inspiring. It suggests a universal interconnectedness that transcends the local, a fundamental relatedness woven into the fabric of space itself. Philosophically, this forces us to reconsider our significance. Are we the center of a lonely universe, or are we participants in a vast, dynamic network whose full story is still being written? The cosmic web implies that our local existence, our planet and our star, are products of a grand, cosmic scale process that required the entirety of this network to function. The iron in your blood and the calcium in your bones were forged in stars that lived and died because gas flowed along these specific filaments billions of years ago. Your very existence is a direct consequence of this immense architecture. This idea of a hidden network binding all things resonates deeply with human culture. Ancient mythologies spoke of a world tree connecting different realms of existence. Spiritual traditions contemplate a universal oneness, a web of life where everything is linked. While science offers a physical, evidence-based framework, the thematic parallels are striking. It shows how humanity, across time and culture, has instinctively reached for this concept of connection, and now we are finding its real, physical counterpart etched across the sky. This intersection of science and culture is powerfully creative. The cosmic web's ethereal beauty, with its luminous filaments and dark voids, has inspired breathtaking digital art, symphonic music, and profound literature. Artists are drawn to its representation of both structure and emptiness, using it to explore themes of relationship, isolation, and the sublime scale of the cosmos. To stand before an image of the cosmic web is to feel a sense of wonder that transcends language, a feeling that bridges the gap between data and emotion. This broader perspective enriches the entire scientific journey, reminding us that our quest to map the darkness is not just a technical exercise. It is a deeply human endeavor to understand our context within the whole of existence. It cultivates a necessary humility, coupled with an insatiable curiosity about the vast unknowns that remain, and this naturally leads us to a pivotal question. If the cosmic web dictates the growth and fate of galaxies, what role does it play in the emergence of life itself? Does this universal architecture create islands of habitability, or is it merely a silent backdrop to our accidental existence? This grand architecture of the cosmos may be the ultimate stage for life itself. The cosmic web does more than shape galaxies. It potentially creates a map of habitability, influencing where life could emerge and thrive across the universe. Consider a galaxy fortunate enough to reside within a dense, bustling filament. Here, the constant flow of fresh gas fuels vigorous star formation, leading to a high production of heavy elements like carbon, oxygen, and iron, the very building blocks of planets and life. This dynamic environment might spawn countless planetary systems, increasing the statistical chances that a few would orbit within their star's habitable zone. Yet this galactic metropolis has its dangers. The same stellar density that builds planets also brings a higher risk of nearby supernova explosions. These cataclysmic events can bathe entire planetary systems in lethal radiation, potentially sterilizing worlds that were once promising cradles for life. Now, journey to the other extreme, to the profound isolation of a cosmic void. Here, a quiet, aging galaxy drifts in near total solitude. Star formation has long since dwindled, and the stellar population is old and stable. Planetary systems in these regions would enjoy a remarkable peace, largely shielded from the violent gravitational encounters and sterilizing radiation bursts that plague the crowded filaments. Life on a world in this ancient calm could have billions of undisturbed years to evolve and complexify. However, the trade-off is a potential lack of resources. The very elements necessary for life, forged in stellar explosions, might be in shorter supply in these quiet, underdeveloped regions. The Webb even regulates the flow of cosmic radiation across intergalactic space. The magnetic fields woven through its filaments act as a labyrinth, scattering and redirecting the most energetic particles. A planetary system's location within this vast network could determine its exposure to this constant, background rain of radiation, which can either trigger genetic mutations that drive evolution or deliver doses that are simply too destructive for life to persist. While still a deeply speculative frontier, these ideas forge a powerful link between the largest structures in existence and the most intimate questions about our own origins. The search for life is no longer confined to a single star or galaxy. It is expanding to consider the address of that star within the cosmic web. Could this universal architecture one day guide our telescopes toward the most promising neighborhoods in the cosmos, the regions where the conditions for life are most perfectly balanced? This grand architecture of the cosmos belongs to everyone, not just scientists in observatories. Bringing the cosmic web to the public transforms an abstract concept into a shared source of wonder and inspiration. Planetariums are at the forefront of this effort, using their immense domes as cosmic canvases. Inside these theaters, you do not just hear about the web, you are enveloped by it. Fly-through simulations take you on a journey across billions of light years, soaring along dark matter filaments and diving into the profound emptiness of cosmic voids. This immersive experience makes the sheer scale and beauty of the structure feel tangible. Documentaries and interactive websites build on this, translating complex data into stunning visualizations that you can explore from your own home. These tools are vital for scientific literacy, demystifying the universe and empowering people with a deeper understanding of our place within it. But the engagement goes far beyond passive viewing. Citizen science projects have opened the doors for anyone with an internet connection to become a cosmic cartographer. In initiatives like Galaxy Zoo, millions of volunteers have helped astronomers by classifying the shapes of distant galaxies. This collective effort is not busy work. It provides the invaluable human pattern recognition that even advanced algorithms can miss, directly contributing to the maps that trace the web's structure. This public participation makes cosmology a truly collective human endeavor. In classrooms, educators are weaving these discoveries into new curricula. Students are no longer just memorizing planet names. They are using real data to explore how galaxies cluster, discovering for themselves the environmental rules that dictate a galaxy's fate. A simple classroom exercise, plotting galaxy positions to reveal a hidden filament, can spark a lifelong curiosity about the universe. This foundational knowledge is crucial, for it builds the public support and inspires the future generation of astronomers who will one day solve the web's remaining mysteries. When we share the cosmic web, we are not just sharing facts. We are inviting everyone to look up and feel that profound connection to the vast, hidden architecture of everything. Our journey through the unseen web reveals a cosmos of breathtaking connection. This exploration has taken us from the ghostly pull of dark matter, the universe's hidden architect, to the strange, repulsive force of dark energy stretching the very threads of reality. We have seen how galaxies are not isolated islands, but vibrant cities linked by flowing rivers of gas, their fates written by their address within this grand design. Through the lens of redshift surveys, gravitational distortions, and colossal computer simulations, we have learned to trace the outlines of this dark skeleton, mapping the invisible architecture that binds everything. This cosmic tapestry does more than deepen our scientific understanding. It stirs a profound sense of wonder about our own tiny place within an immense, dynamic network. The quest is far from over. With every new telescope and each fresh simulation, we stand at the threshold of deeper revelations, ready to illuminate more of this magnificent hidden structure. Thank you for venturing into the unseen with us. We would love to hear what part of this cosmic web captivated you most. So please share your thoughts in the comments below.